Bismillah ar-Rahman ar-Rahim. We are interested in this summation, sum n from 1 to infinity, the square of the nth harmonic number divided by n squared. We want to show that this sum is 17 pi to the power 4 over 360. The nth harmonic number, hn, is the sum k from 1 to n 1 over k. This is 1 over 1 plus 1 over 2 all the way to 1 over n. We can write down 1 over k as the integral from 0 to 1 of x to the power k minus 1 dx. We can then interchange the order of integration and summation. We have a geometric series. We can write h of n as integral from 0 to 1 of 1 minus x to the power n divided by 1 minus x dx. Let's do integration by parts. We write down this integration as integral from 0 to 1, 1 minus x to the power n d minus log 1 minus x. We will have a term 1 minus x to the power n log 1 minus x with a minus sign, and we need to take the limit as x tends to 0 and as x tends to 1. As x tends to 0, we have no problem. This will be log 1, which is 0, and 1 minus 0 is 1, so there is no problem. But if x tends to 1, then this logarithm will tend to minus infinity, and 1 minus x to the power n tends to 0. The integral will be integration from 0 to 1, and then we have log 1 minus x. We need to differentiate this guy. We get minus n x to the power n minus 1 dx. Before proceeding, let's resolve this limit here, and the good news is that it is equal to 0. Let's see how. Write 1 minus x to the power n as 1 minus x, and then the series 1 plus x squared all the way to xn minus 1. If we put x equal to 1 here, there is no problem. We just get n. And let's rewrite the product of these two terms as log 1 minus x over 1 minus x. The numerator tends to minus infinity as x tends to 1 from the left. The denominator tends to plus infinity as x tends to 1 from the left. We are in an infinity over infinity situation. We can apply L'Hopital's rule. The derivative of the numerator is minus 1 over 1 minus x. The derivative of the denominator is 1 over 1 minus x squared. We can have the minus sign here outside, and the remaining term is 1 minus x, and when x tends to 1, this is equal to 0. This term disappears, and we are left with this integral. Note that there is an n here. I will join it with h of n. So now we have this useful representation of h of n divided by n. The nth harmonic number divided by n can be written as minus the integral from 0 to 1 of x to the power n minus 1 log 1 minus x dx. Note that our summation involves h of n divided by n all squared. We will square both sides. hn divided by n squared will be the double integral of x to the power n minus 1, y to the power n minus 1, log 1 minus x, log 1 minus y, dy dx. Our sum is the sum of this double integral here. Can again interchange the order of summation and integration. These two terms can be joined as x, y, all to the power n minus 1. And this is a geometric series that can be summed if we interchange the order. And the sum will be 1 over 1 minus xy. Our summation of interest is now written as a double integral. Let's focus first on the integral with respect to y. So here we have an outer integral with respect to x. Log 1 minus x. Let's take it outside. And our initial focus is this integral from 0 to 1. Log 1 minus y over 1 minus xy dy. We will do a change of variables. Specifically, we use u equal to 1 minus xy. We are changing y to u. Du is minus x dy. So let's do this change here. Dy is minus 1 over x du, then log 1 minus y. If u is 1 minus xy, then xy is 1 minus u. 1 minus y is 1 minus 1 minus u divided by x. The denominator 1 minus xy, that's u. Let's see the limits of integration. If y is equal to 0, then u is equal to 1. And if y is equal to 1, then u is equal to 1 minus x. We can use this minus sign to have the integral from 1 minus x to 1, log 1 minus u over x, and then we have u in the denominator, du. There is a dx here. We need to spend some time thinking about this integral. The argument of the logarithm can be written as x minus 1 plus u divided by x, and this can be written as the difference of two logarithms, log x minus 1 plus u minus log x. We can do this integral of log x. We have integral from 1 minus x to 1 of log x over u du. This will give us minus log x log u, and then we have, here is the upper integration limit 1, and the lower one is 1 minus x. If u is 1, that's 0. And if u is 1 minus x, we get plus log x log 1 minus x. So we have this term here, but we have another logarithm and another integral. What we will do is another change of variables. Now we use w is equal to u divided by 1 minus x. Du becomes 1 minus x dw, and u is 1 minus x times w. du over u is dw over w. The argument of the logarithm is now x minus 1 plus w times 1 minus x. When u is equal to 1 minus x, w is 1. And when u is equal to 1, w is 1 over 1 minus x. Look at this logarithm here. We can write it down as log, and then we can have 1 minus x as a common factor, w minus 1. And write this as log 1 minus x plus log w minus 1. Log 1 minus x divided by w is readily integrable. When we do this integration, we get log 1 minus x multiplied by log w. If we use the lower limit of integration, we get 0. And if we use the upper limit, we get minus log 1 minus x. So this integration here will give us minus the square of log 1 minus x. Then this is the integral that we need to handle. Integral from 1 to 1 over 1 minus x log w minus 1 over w dw. Our integral of interest can be expressed in terms of the Dilogarithm function. The Dilogarithm function, Li2 of z, is this summation n from 1 to infinity, z to the power n divided by n squared. And this is when the magnitude of z is less than or equal to 1. As an integral, the Dilogarithm function is minus the integral from 0 to z log 1 minus u divided by u du. We want to show that our integral of interest is minus the Dilogarithm function and then these two terms. We will prove this by defining g of x. That's a function whose domain is the open interval from 0 to 1. The codomain is the set of real numbers. We will define g of x to be our integral of interest, and then we have minus this term plus this term, and then we add the Dilogarithm function. We want to show that g of x is equal to 0. If we show that g of x is 0, then it means that the integral is indeed equal to this right-hand side. So that's g of x. Let's differentiate using Leibniz rule for differentiation under the integral sign. When we differentiate this integral here, we differentiate 1 over 1 minus x with respect to x. That's 1 over 1 minus x squared. Then we replace w, the dummy variable of integration, by the upper limit. So we have log 1 over 1 minus x minus 1, and then this w is replaced by 1 over 1 minus x. Can eliminate the square. We have 1 minus x in the denominator, and then this log 1 over 1 minus x minus 1. This is 1 minus x in the denominator, and then in the numerator we have x. This logarithm can be written as log x minus log 1 minus x. For the second term in the function g of x, the derivative here is minus half times 2, and then we need to differentiate log 1 minus x. The derivative is minus 1 over 1 minus x. We end up with log 1 minus x divided by 1 minus x. For this term, we get minus log x over 1 minus x plus log 1 minus x divided by x. Finally, this is the integral representing the Dilogarithm function. And for this integral, we differentiate x with respect to itself. That's 1. And then we replace u by x. Note that these two logarithms cancel. And then these other two can be combined as 1 minus x, log 1 minus x, minus log x. This is exactly this term here, but with a minus sign. G prime of x, the first derivative of g with respect to x, is equal to 0. G is a constant function, and we can know the value of the constant by investigating the limit of g of x as x approaches 0 from the right, from the positive side. For this integral, as x tends to 0 from the right, the domain of integration shrinks, and this will be 0. When we put x equals 0 here, we have logarithm of 1, that's 0. And for the Dilogarithm function, it's clear from the series representation that it approaches 0 as z tends to 0 from the right. We are left with this term here. If x tends to 0 from the right, then log x tends to minus infinity, log 1 minus x tends to 0. We can apply L'Hopital's rule to obtain the limit of this term here as x tends to 0 plus. We can write it as log x over 1 over log 1 minus x. Log x tends to minus infinity as x tends to 0 plus. And 1 over log 1 minus x tends to minus infinity as x tends to 0 plus. Infinity over infinity situation by L'Hopital. The derivative of the numerator is 1 over x, and the derivative of the denominator is minus 1 over 1 minus x, and then minus 1 over this logarithm squared. Rearranging the terms, this guy just tends to 1 as x tends to 0. Then we have this ratio here. If x tends to 0, then we are in a 0 over 0 situation. We can reapply L'Hopital's rule. The denominator becomes 1 after differentiation, and the derivative of the numerator here is 2 log 1 minus x, and then the derivative of log 1 minus x, which is minus 1 over 1 minus x, as x tends to 0. This logarithm will take us to 0. So the constant is equal to 0. This function here is equal to 0. showing that this integral is indeed equal to these three terms. Let's examine our situation. This is our sum of interest. We started by representing it as a double integral. We focused on this integral here. We have shown that this integral is this integral from 1 to 1 over 1 minus x log w minus 1 over w dw, and then these two terms. This integral can be written as these three terms, including the Dilogarithm function. So let's take these three guys and put them in place of this integral. Note that this term here and this term will cancel. We have here minus log 1 minus x squared. Here we have 1/2. These two guys can be combined as minus 1/2 log 1 minus x whole squared. And then we have the Dilogarithm function. This is the inner integral here. So let's insert it and carry out the last step of integration. We have two integrals. Let's start with this integral first. Recall that the Dilogarithm function is minus the integral from 0 to x log 1 minus u divided by u du. What is the first derivative? Like we have done on the previous page, this is minus log 1 minus x divided by x. This is exactly this term here, which means that the result of this integration is 1/2 the square of the Dilogarithm, and then we use our limits of integration. At 0, this is 0. At 1, if you put x equal to 1, then this is zeta of 2. The sum n from 1 to infinity 1 over n squared, which is pi squared over 6. This integral here is zeta 2 squared, that's pi squared over 6 all squared, times 1/2. That's pi to the power 4 divided by 72. We are left with this integral. We have minus half integration from 0 to 1 log 1 minus x cubed divided by x dx. Change x to 1 minus x. So we have minus 1/2 integral from 0 to 1 log x cubed divided by 1 minus x dx. We are done if we evaluate this integral here. Recall the result that if we multiply log z by z to the power alpha, and alpha is strictly greater than minus 1, and then integrate from 0 to 1, if we do integration by parts and take the limit, we end up with minus 1 divided by alpha plus 1 squared. So this is a known result and a very useful result. Integral from 0 to 1 z to the alpha log z dz is minus 1 over alpha plus 1 squared. Now differentiate both sides with respect to alpha. The right-hand side becomes 2 over alpha plus 1 cubed. And here, when we differentiate with respect to alpha, we differentiate under the integral sign, this z to the power alpha. Its derivative is z to the power alpha log z. So we end up with log z squared. The integral from 0 to 1 of z to the power alpha log z squared is the derivative of this guy with respect to alpha, 2 divided by alpha plus 1 cubed. Let's do another step of differentiation with respect to alpha. This term here on the right-hand side becomes minus 6 over alpha plus 1 to the power 4. And when we differentiate this guy here, z to the power alpha will give us z to the power alpha log z. So we get integral from 0 to 1, z to the power alpha log z cubed. This is minus 6 over alpha plus 1 to the power 4. This integral here can be used to evaluate this integral. The idea is that we will expand 1 over 1 minus x. So this is minus 1 over 2, integral from 0 to 1 log x cubed. And then 1 over 1 minus x, this is summation, let's say j from 0 to infinity, x to the power j. According to our rule here, if we interchange the order of summation and integration, we end up with minus half summation j from 0 to infinity. And then the integrals will give us minus 6 divided by j plus 1 to the power 4. Minus 6 and minus half, that's 3. And then we have summation j from 0 to infinity, 1 over j plus 1 to the power 4. This is exactly zeta of 4, which is pi to the power 4 divided by 90. This integration here is pi to the power 4 divided by 30. That's it. We can now combine our results. We have pi to the power 4 divided by 72, pi to the power 4 divided by 30, and their sum is 17 pi to the power 4 divided by 360.